Hey, geometry, this is Mr. McCune. We're going to solve some problems together from the Common Tangents chapter that was 8.3. These are all from page 253. We're going to see how we do. I know some of these were some of the more confusing problems we ran into in class, so we'll take a look at some of them together. We'll start with, this is number 1 from page 253. So number 1, we have this diagram here, and let's label our points. We have A, B, C, D, and E. We are given that this radius is 10, AE is 10, and that BD is 5, that BC is 12, and we want to find AC. All right, now the way that I solve this is using proportions of similar triangles. If you if you think about this, we have two triangles that are similar. We have the big triangle AEC, and then the smaller one BDC, and you could rewrite this as two triangles. So if I did a crude drawing right here, let's see, I could do that's AEC, and then our smaller one is DBC. So you can right away see that we're going to have similar triangles. And why do we have that? Well, they share angle C in common right here. And we also know that we have a radius and a tangent, which means these are both right angles. So right away we have angle-angle. So to write it down here, on these we have angle-angle similarity between these. And once we have similar triangles, we can use our rules of proportions. We can use the fact that the similar corresponding parts of similar triangles are in proportion. So AE over AC equals BD over BC. To substitute in, 10 over AC equals 5 over 12. We cross multiply, 5AC equals 120, and our solution would be AC equals 24. Easy enough, right? All right, let's look at the next one. The next one was number 3. Number 3, once again, we have A, B, C, D, and E. These points E and D, are radii. Radii is a fun word to say, by the way. Fun word to spell, actually, 2 I's in a row. I think the only other place that happens is in the word Pompeii. But let's go ahead and label the radii 10, 5, and 12, and we are asked to find CD. All right, CD is the portion, is what will end up being the hypotenuse of the smaller triangle. Remember, we have radii in a point that have a point of tangency with this tangent ray here, which means we have right triangle, so across from the right triangle will be the hypotenuse. So CD right here, that's a hypotenuse of a right triangle, and we have the other legs. So this one is actually pretty straightforward. We have CD squared will equal 5 squared plus 12 squared, and we can work that out. 5 squared is 25 plus 144. CD squared equals 169, so CD will equal 13. Next one, number 5. Let's change up the colors just for fun. Let's go blue. Number 5, we have A, B, C, D, and E, but we've changed up the numbers a little bit. Now AE is 9, BD is 3, and BC is 4. We are asked to find ED. Now this one is a little more involved. And there actually are a couple ways you could go about solving this one. I'll just show you the way that I did, and maybe you can see another way to do it. Well, the first thing I did was I found CD. Now remember, CD is the hypotenuse of the smaller triangle. And the reason I wanted to find that is ED down here, that's what we're looking for. ED is part of the hypotenuse of the larger triangle. And remember, these triangles are similar, and we can use rules of proportionality to find it. So if I know CD, if I can find CD, and if I can use rules of proportionality to find EC, that hypotenuse, then I just subtract and I can find ED. So let's find CD. Well, CD squared equals 3 squared plus 4 squared. And when we work that all out, we will eventually get CD equals 5. That's what it'll simplify to. And you might recognize that as one of our special right triangles. So CD equals 5. Now that we have that, we can set up a solution. All right, so if CD equals 5, let's look at what EC equals. EC equals ED plus CD, right? EC equals ED, the piece that we're looking for, plus CD, which we just found right here. Let's also set up a proportion. AE over EC, so that's the radius of the bigger one. The radius of the bigger one over its hypotenuse equals the radius of the smaller one, BD, over its hypotenuse, which is CD. Well, now we have enough information that we can substitute. We know the hypotenuse, or we know the radius, AE. We know EC because we just defined it right here. And we know BD from the diagram, and CD is given. So we'll just substitute in all that information. So now we'll have 9 over ED plus CD. Well, what is CD? CD is 5. So ED plus 5, and that will equal BD over CD, which is 3 over 5. We'll cross multiply. We'll get 3 times ED plus 15 equals 45. We'll use our algebra. 3 ED equals 30, and ED equals 10. So to back up a little bit, that one involved a couple steps. We first had to find CD, but in the end we used proportions and similar triangles. And to use similar triangles, we had to recognize that we had a radius that is perpendicular to a tangent. And that helped us find our similar triangles by angle-angle similarity. All right, next one. Number 4. These are fun. All right, we have 2 circles that are tangent to each other. That's given. That's important because we have one point of tangency right here. All right, we are given these points. We are given point S, point T, point V, and point U. And I'm sorry, I forgot to mention, this is we are now on number 11 on page 253. So this is number 11. All right, now these are going to be, there's going to be a whole series of problems that look like this. And we'll see they have very similar solutions each time. This is a great one. This is going to be a great one to study. A couple things that we want to recognize right off the bat that are going to help us. First is we need to find ST. That's helpful. Read the directions. What are we looking for? All right, we're looking for ST, which is this tangent segment on the outside. Points of tangency at S and T. Well, what does that mean? If we have tangents and radii, well, we've got right angles there. That's important. That's going to help us. We're also given the lengths of these radii. We know that SU is 9 and TV is 3. That is given to us. All right, now we need to find ST. How in the world are we going to do that? Well, there's a couple relationships that we can set up here that will help us out. Let's see. I am going to first draw a line between the centers. I'm going to change colors here to hopefully make things a little more clear. All right, we're going to draw from U to V right here, go straight through the center. Now, one thing to recognize about that line segment that we just drew is that that is the radii, the sum of the radii, right? To that point of tangency right in the middle, that's really 9 plus 3. So UV equals 12. That's something that will be helpful to us right off the bat. So look for that. That will be something that is implied that you'll have to find. All right, now the next thing I'm going to do is draw a rectangle. This is going to be really helpful to us in solving. So let's go back to our dotted line, and I'm going to draw a rectangle straight across from the small radius, starting from the center of the smaller circle to the bigger one. Now what does this do for us? Well, now we've got a rectangle here. And notice that we also have a right triangle right here, this piece. And there's some information we know. This far side of the rectangle is going to be 3. So what does that mean that the part closest to the center is? Well, this piece will be 6. And you probably recognize by now that we have a right triangle in the middle. That right triangle, its larger leg that I'm dotting in blue right here, that has the same measure of ST because it's the opposite side of the rectangle. So a whole lot going on here. But if we keep things straight, in the end, essentially we have a right triangle where the short leg is 6, the hypotenuse is 9, and the longer leg is the measure of ST that we're looking for. So from this point, or I'm sorry, I just said it was 9. As you were following along, you realized that it is not 9, but the hypotenuse is 9 plus 3. It's the sum of the radii, so it is 12. Oh, and you might also recognize at this point that this is a 30, 60, 90 triangle, where the smaller leg is half of the hypotenuse. So we can work this out with Pythagoreans, or if we recognize our 30, 60, 90 relationships, ST equals 6 radical 3. But that should be enough of a setup for you to be able to do this on your own. Okay, next one. This is number 13 on page 253. Hope you're having a good weekend. No ice yet, but it may be coming. Who knows? Take a second, pause, stretch, go run around a little bit. All right, number 13, Mr. McCune's lucky number. All right, we change up the numbers on us here. Let's label our points again. S, T, we have V here, and U down at the base. We are given that ST is 24. We're given that this radius is 16, and we're given that this radius is 9. We are also given that UV is 25. And we are asked to find VT. So I kind of jumped the gun there and gave us the answer. We don't know that VT is 9 yet. That is what we are looking for. Now this one, they give you a lot of information on here, and I guess there are ways you could solve this using the box. You could draw a rectangle, and it's good to get in the practice of recognizing when we need to draw a rectangle. And you might notice that drawing a rectangle, that rectangle that we just drew, which becomes the base of this new triangle that we've created here, that's going to have a measure of 24 because that is the measure of ST. The hypotenuse is 25, so that would let us find this small leg right here. If we found that small leg, we could subtract it from 16, And that would be this measure right here, this little piece, and that would equal the radius VT. But there is a much, much simpler way to do this. If you notice the section UV equals 25. Now, what is going on between in the section of UV and the big circle? Well, that's just the radius of the big circle, right? So UV, we could also express UV is the sum of US plus VT. Do you see that? It's really the sum of the radii. So if we do our algebra, VT will equal UV minus US. So we plug in, we substitute, VT equals 25 minus 16, and VT equals 9. Again, you could solve that by making a rectangle, but recognize that the radius can be brought down like that. All right, 2 more. Hope you're still hanging in. All right, this guy is number 17. We have C, A, P, B, and D. All right, and we can instantly fill in. We should recognize this immediately now that if we have a radius and we have lines tangent to that radius, they meet at a point of tangency, then we have right angles. That's going to be very helpful for us. Well, this is a proof. They've asked us to do a proof, and we are asked to prove that angle PCA is congruent to angle PDB. PDB. So the angles that we are looking to prove are here and here. So let's set up a table. Statement, reasons. Number 1, let's start by looking at the fact that we just drew right angles. Well, what let us do that? That's because a radius and a tangent form right angles. So we can say that angle A and angle B are 90 degrees. Why? Because it is a radius and a tangent. I know that's not the proper postulate. You can look in your book for the exact way to represent that, but essentially a radius and a tangent gives us 90 degrees. So we can then say that angle A is congruent to angle B. Why is that? Well, that's the definition of angles. They're both 90, right? So the definition of angles. That's one of those obvious lines that you're like, I really have to write that? All right, step 3, if we could find one more angle in common, well then we'd have similar triangles. So here we go, we got vertical angles right here. So angle P is congruent to angle P. Why? Vertical angles. And finally, step 4, well I guess we're gonna end up having 5 steps here. Step 4, we can set the triangle similar. So triangle PCA is similar to triangle PDB. And they're similar by angle. So at last, we can say that angle PCA is congruent to angle PDB because the corresponding angles of similar triangles are congruent, or the similar parts of similar triangles. So that's really the definition of similar triangles. All right, a proof for you on your weekend. Last one. This one is a lot of fun. You are given this triangle with 3 metal discs, and you are given a radius of 10 for each one. And you are asked to find one side length. How in the world are we going to do that? Oh, one more important bit of information. We are given that this triangle is equilateral. This is an equilateral triangle. So all these pieces are congruent, and that therefore all the angles are congruent, and they are 60 degrees. That is very important, as we'll see in a minute. Now, how would you start this one? This one I had to think about for a while, and I liked it. It was a good challenge. And the trick is with the radii. You're going to split up the pieces of the edge of the triangle into some parts. And I'll kind of tick them off here. Get that little piece. Now check out what we can do. If we draw the radii to the center of these two, we know that each side is 10. So that piece right there, which now forms a rectangle, and we know that it's a rectangle because the sides of the polygon are tangent, so we have right angles where the radii hit. Well, we just formed a rectangle with the 2 halves being 10 each, so this piece will be 20 from here to here. So we've already started building the side of this triangle. That piece is 20. Now, where can we find the other piece? Well, check this out. Let's look up here. I'm going to erase that real quick, and I'm going to pull out another color. I'm going to draw this line right here and create for us a right triangle. Remember, this is also a right triangle right here. Now, if I'm going from the center of this circle to an equilateral triangle, well, I've just bisected that angle in the corner. So this is 30 degrees. This is 90 right here. So that means I have a 30, 60, 90 right triangle. I know that this radius is 10. So therefore, this long leg must be 10 radical 3. And if that's 10 radical 3, and this is an equilateral triangle, then guess what? We have the same situation going on over here. So this piece is 10 radical 3. You put that together, and the side of this triangle is 20 plus 10 radical 3 plus 10 radical 3, which is 20 radical 3. Hooray! You just did some awesome geometry today. We can't wait to see you guys after the weekend. Hope you enjoy it and get out and find some fun, find some sun, and some good friends. All right, see y'all later.